Hello, mother lovers. Let's have a look at paper 3, shall we? So, first one, we got suvat. We need to find the maximum height of this thing as it goes up. So, what's the max height going to be? We don't know. The initial speed of it was that 14 going up in the air. To find the max height, we need to find basically when the velocity is 0, yeah? And then the acceleration minus g, and we don't care about the time at all. So, without the t, what do we need? We need v squared is u squared plus 2as. Summing this all in then, v squared is 0 squared, so that's just 0. U squared, 14 squared, 196. 2as, so it's 2g, so minus 2g, times by the s. So s itself then will be 98 on g. G, 9.8, so it should be 10. If I can get blue. Lovely, looks good. Now then, find the time when the speed is minus 10.5. So doing that again, another suvat, we can copy some bits over. What we're going to have this time, we don't care about the position of it at all. We do, however, care about the time. G is still G, U is still 14. The V, however, now though, is going to be the minus 10.5. So in this case, we don't have the S, so we want V is U plus a T. We want T though, so we can just rearrange straight away if you like. V minus U over the A. Plugging everything in, V minus 10.5. U will be 14. On the bottom then, we're going to have minus G. So when we plug that all in together in the calculator, what we're going to have minus 24.5 on the top, minus G on the bottom. Those minuses obviously cancel out. And what we're left with is 2.5. Just check that on the calculator, make sure it is the right way around. 24.5 divided by 9.8, 2.5. Lovely, jubbly, looks good to me. So question 1, not too bad. Nice, easy start for it, wasn't it? Let's go number 2. Here, so we've got given some information. I don't know exactly how you're given all this stuff. I'm just trying to piece it back together from the answers. So we've given some velocity. We're told the speed when the time is 8 is 4 root 5. The position at time is 1 is given by this vector. And we're told that the c, which is the unknown in this velocity part, is positive. So let's keep going. What do we need to do first? Find c. So we have the velocity vector and we have the speed at time is 8. So let's go and find out what that speed, well, let's plug in when time is 8, what do we get? So top one, we're going to have 8 squared divided by 8, so it's just 8, yeah. And on the bottom, we have the cube root of 8, which is 2, and then times by that negative c. So minus 2c. We want the, it's not very good to see, is it? Try again. We want the speed of this thing. So speed when time is 8 is going to be 8 squared, 64, plus 4c squared. And that got equal to 4 root 5 all squared. So 4 squared 16 times by the 5 gives us 80. So the 4 squared is 16. C squared is going to be 4. And therefore C is going to be plus or minus 2. But we know that we have C being positive. So this tells us that C is 2 in the end. Looks good. Now then, find the acceleration. So to do that, we're going to have to go through and remember the acceleration is the rate of change of the velocity. So doing that, what we're going to have, top row, bring that 2 down, so we'll have a quarter of just t. And then for the bottom row, remembering that c is 2, so we're going to have 2 times a third, so minus 2/3 on there. And, oh, not c, sorry, we have t. And that 1/3 would have dropped down to negative 2/3. Looks good to me, let's just double check. Yep, looks good. So that's nice. Let's circle that one. Part C then, we need to find the position velocity, position vector. So let's do that. We need to integrate, in this case, the velocity vector. So doing that, top row, we're going to raise the power to 3 and then divide by the 3. So we're going to have t cubed and then 1 over 24. On the bottom, raising that power gives us t to the 4/3. So doing 3/4 of minus 2. So times that by minus 2, minus 6 on 4. So we're going to have minus 3 on 2 for that bit. This though, we will have some constant of integration. I won't use C because we've used it already in the question, so I'll use a K this one. And we're given the position when time is 1. So we can sub that all in, like plugging in the value of 1 into here. What we're going to get is, so you just look at the coefficients, don't you? It's 1 over 24 and minus 3 on 2. We'll still have the plus K. And that should equal to the 13 on 29 and minus 1. So what we can see from that, if we do the 13 on 29, take away 1 on 24, what do we get? We get a number that's not the answer. What we've done wrong there? Should be a half. What's happened? Oh, sorry, this is on 20. I've written that down wrong. This should be on 24 as well. That makes more sense, doesn't it? 24. So down here, that should have not been 13 on 29, but 13 on 24. If we change that over, we get a half. Yeah, that's good. So where's the number wrong? That one. Should be a 4. So K ends up being a half and a half. So plugging it all back in together, what we're going to have for R? Well, we still have the 24th of t cubed, and I'm going to add a half to that, and then we'll still have the minus 3 on 2, t to the 4 on 3, and then still plus a half to that one. Lovely, looks good. We want the bearing when t is 8. So bearing, you need the velocity, you need the angle, basically, when t is 8. So to do that, what we're going to do, let's take the velocity vector and plug in when t is 8. Well, we've already done a lot of stuff, haven't we, with 8, so we know this. So the velocity when it is 8 is going to be 8 on the top, and we knew c was 2. So we have minus 4 in that bit. It's often better to draw these out, like what's happening. We're going 8 to the right, 4 down, yeah? So we want to find effectively this angle, don't we? So thinking about that, we have opposite of 4, adjacent of 8. So tan of theta will be a half. Using that then, what we're going to get theta is 26, 27 if you round up correctly. But we always want to measure from north, don't we? So we'll add 90 onto that. So the bearing is going to be 90 plus 27, or 107. No, 117. So I can do numbers. 117. Lovely, looks good. Circle that one. Circle this one. Just have a quick double check. Yeah, 117. A half and minus that bit. Yeah, that's good. That's good. That's good. This one was spot on. I'm assuming that one's spot on as well. Yeah. Lovely. All looks good to me. Number 3 then, we had some slope. I've drawn this slope correctly. It's tan of 4 on 3. Like, you don't kind of realize how steep how steep that slope is. So what do we want to do? I don't know how this x is given to you. If it's given to you pointed from the left into the right, always just move it. You always want to have the tail of the arrow at the actual center of the object that you're dealing with. We told its mass was 2/5, and we've got gravity coming down. So we can write on there that we're going to have 2/5 of g coming down here. So 2g on 5. We'll have some reaction force because we're touching a slope. That will come up there, perpendicular to the slope. And we were told we have friction. We're at the point of slipping up the plane. So our friction is going to be pointing down the slope. So half of r in this case. That's good. Question then asks for r and x. That's all you can really find from here, isn't it? I suppose you could find the friction if you wanted to, but that's just half of r. So what do we want to do? Well, if we want to find r straight away, what unknowns do we have? We have r, we have x, and we have, obviously this is half of r. So if we pick like this, what I can do is I'm going to recolor these ones black actually. So we color these black, or let's color that blue and color this blue. And then what we can see, we have like the double axis thing. If I just keep going through, so like that. So our angle that we were given in the question is between the horizontal and the slope. Horizontal slope. So it's in that little crevice. And then it's going to alternate round. And we have x on the blue set. So what we can, well, on this horizontal version. So if we actually just take vertical components, it will eliminate x straight away. We'll be left with just r's in there, which is quite nice. So let's do that. Taking the vertical then. And we know that we're in equilibrium, so we can just do up and down straight away. what do we have? Well, we're going to need to have R going up, angles in between, so it's going to be cos. So our cos of this, let's figure this out as well. Cos is going to be the adjacent, which is the bottom, so 3/5, and sine will be the other one, 4/5. The 5 comes from, like, think about the triangle 3, 4, 5. If this is 3, this is 4, this would be 5. So this is good. We needed R cos, didn't we? So that's 3/5 of that one. Anything else pulling us up? Nope. Pulling us down though, the weight goes just straight down, so 2g on 5. And then the R, or half of R, but we're going to need to have the vertical component. There's no angle in there, it's over here, isn't it? So it's sine, so 4/5 of this. So half of 4/5 is 2/5, so 2/5 of R. Looks good. We got 3/5 this side, 2/5 that side. Let's make it just have 1/5 on the left. And then we can get rid of all the fifths as well, can't we? So R is just going to be, well, let's just write a new line. R will be 2g. That looks good. Friction then we know would be 1g, yeah, just coming down here. Next part of the question then, let's find x. So in a similar sort of way, we want to eliminate as many things as we can, but we know everything now, so it doesn't really actually make a huge difference. Nicest way to do it then is just make x be one object and without any sort of sines or causes. So if we go horizontally, x is pulling us to the right, and then what we've got pulling us to the left, let's look at this r to begin with. We know above we used cos, so it's going to be sine this time, but we can do it again. This angle, we want to have this direction. The angle's not in there, so we need sine, so it's 4/5 of r. And actually, we know r is 2g, yeah, so we can put that straight in. So it's going to be 4/5 of 2, which is 8/5, so 8g on 5. That should equal that, sorry. And then also putting it to the left is going to be the friction, but times by cos. So that was just g, wasn't it, for the friction, times by cos, so 3/5 of g. 3g plus 5, so it looks like 11g on 5 altogether. Was that correct? Let's double check. Double check both bits as well. R was 2g, that's good. And this was 21.56. 11 on 5 times 9.8 gives me 21.56. Looks good to me. Number 4 then, let's see what's happening there. Oh yeah, lifts. Yeah, we got something on a lift, don't we? So the first question asking for the tension in the wire holding the lift up. So in that case, we'll view it as just one big object, yeah? If we take just these two bits of it. Not worried about really like what's happening inside the lift. So like the fact that there is another object in there, we don't really care. This is now not the lift, it's like the entire thing. Do you know what I mean? You can almost like group it together to be like, oh look, we just actually care about them as one object. The lift plus all of its contents. What things do we know about that? Well, they have a total mass of 420, plus 420g coming down. Tension is going to be pulling us up, and we are traveling up at 1/5 of a meter per second, 0.20 centimeters per second. That's our acceleration, sorry, not speed. So 1/5 meters per second squared. So this is good. Let's just resolve the forces up and down then, because we want to be going up. What's pulling us up? Tension. What's pulling us down is our mass, the 420g. And that's going to have to equal the resultant force. So the mass times the acceleration, like without the g in there. So 1/5 of 420 is going to be, is that 80? 420 divided by 5, 84. So this should equal 84 on this side. So T itself then is going to be whatever 420g plus 84 is. Is that right? Looks good to me, I think. Yes. Let's just double check. 9.8 plus 84. We get exactly 4,200. That's always a nice sign, isn't it, when you get a nice whole random like that. They've set it up lovely for us. So that's good. Now then, we want the reaction force between the box and the lift. So in this case, I'm going to take both objects, but I'm going to consider them separately. I don't actually care about how they are related to each other. I just care how those relationships affect them individually. So thinking about the lift itself, it obviously has that tension coming up, which we know is now 4,200. it's going to have its own weight coming down, which was 400. Did I write that down? It was 400 when it by itself, and then it was 20 for the 20 for the thing inside the box, inside the lift. So this is 400. And also, what else is going to be pulling it up will be, sorry, pulling it down will be the reaction force. Because what's lifting the box up is that reaction force. How else is it moving up? Think about when you're in a lift, why do you not just fall through the floor? Because the floor is pushing you back up again. So same thing here, floor pushes you up, you must push the floor down. You are also having some gravity, and that was 20g. And then we're going to resolve these individually. Basically connected particles is what's going on, yeah. But we don't really care how they're connected, but they both have the same acceleration is the thing to remember. So they're both going to be moving with that fifth of a meter per second. They're moving through. So doing this, we'll with simultaneous equations. I'll call this like this is lift. This can be box. So looking at the lift, what's pulling us up is going to be that 4,200. What's pulling us down is 400g and r, and we must be equal to 400 for our mass times by a fifth, so 80. We could have done this with as well with the box, just to show you that it might be easier actually to do it with the box, because we know that we're going to have r pulling us up. Take away the 20g, and that will equal a fifth of our mass, so it's going to equal just 4. Both these should give the same answer. This works quite nicely simultaneously when we don't know the acceleration already. Doing this though, we're going to have r is 20g plus 4, which is 200 exactly, top of my head. Because that would make, like, two of them would be 19.6, so 196 plus 4, 200. Is that right? Looks good to me. Looks good on the mark scheme. Lovely. Let's keep going to number 5. Some projectiles. We're firing something in the air. Don't know exactly what it was. Again, I've done the same angle. Angle's correct, so it's tan. Tan is 3 on 4. Time to hit the ground. Suvat. S. Well, we're on the ground, don't we? U. We have 28 as our initial speed, but that's at some angle. So we have it this way. We want it that way. The angle's not in between, so it's going to be sine. Let's take these and look what we would have. Sine in this case is the opposite, so 3/5, and cos is going to be 4/5. So yeah, we want 3/5 of 28, whatever number that is. 0.6 times 28 is 16.8. I will leave it as 84 and 5, I think that might be easier. 84 on 5, it's not very neat. Try again. 84 on 5. Lovely. The final speed will actually be negative of that, but it's not really that we care about that at all. You could use it that way around, but we've already, like, you need one of these two, really. Either this being 0 or this being minus 84.5. Acceleration is just minus g. And the time is going to be what we're looking for. So without the v, it's going to be s equals ut. So s0 equals u times t. So 84 on 5 times by t minus a half of t squared. So we can factorize that as 0, like the time it took off is the 0, yeah. And as we do this, then we're going to effectively add this one to the other side and divide by g on 2. So it should be 84 on 5 times by 2 on g. That should be our time. Calculating that all together, what we're going to end up with, 84 times 2 is going to be 168 on 5g. What number is that? Let's find out. 168 over 5 times 9.8 gives me 24 on 7. Okay, quite a nice number popping out. So that comes from the other triangle, isn't it? You have like 3, 4, 5 and the 5, the 7, 23, no, 7, 24, 25 one. Is that correct though? Let's find out. It should be 3.43. Is that right? Yep, looks good. Next one then, we're going to find the angle of the velocity when our horizontal position is 48. So, okay, I imagine there was some target there because you want to find the speed of it as well in a second. So for both of these questions, we need the velocity then. Same suvat, but we can change things ever so slightly. So let's duplicate this over. what's going to have changed then is going to be, let's actually quickly note down that this is vertical, because we're going to now need to find like horizontal position being 48, and we want to find the speed of everything at that point. So we need to, first of all, before we can do this one, find the time it takes to get there. Because when we go horizontally, we have no acceleration. So instead of doing a suvat, you just need to do a soot. Like, you don't need the v and the a. Acceleration 0. V is the same as u. We want to find 48, don't we? We had originally used sine to go vertically, so we want to use cos this time. So it's going to be 4/5 of 28. So 4/5 of 28 gives us 112 on 5. I'm always hoping that the fractions will cancel off, which is why I always keep using them. And t is what we're looking for. So speed, distance, time. We want to find the time. Time is going to equal to our distance over our speed. So figuring that out, write that in the calculator. 48 over 112 over 5. What does that give us? 15 on 7. Again, very nice and satisfying. Like this coming out over 7, this coming out over 7. It doesn't look like it should really, does it? Like, looking at it, like the 7's probably, it's coming from here and at the 7, but like it's always a good sign that it is appearing in multiple places. So that's good. We now then take that and we will sub that into a suvat for this one. So the time that we have now is not unknown, but it is that 15 on 7. G is now not going to be, no, G, it still will be that, sorry. We want to find the velocity. And we don't care about the position. So when we don't care about position, v equals u plus at, and v is what we're looking for. So v is going to be u, 84 on 5, plus at, so minus 15 on 7, lots of g. Doing that then, what do we get? 84 on 5 minus 15 on 7 times 9.8, and I get an answer of minus 21 on 0.5. No, 21 on 5, sorry. So minus 10.5, that is, isn't it? Yeah. Minus 4.2, sorry. Minus 4.2. Lovely. Is that good? Yes. Yes, it is. We also, though, however, need the... Oh, I suppose we have the other one, don't we? Yeah, it's going to be this value over here. So we have 21 on 5, and we have 112 on 5. So let's draw that out as a triangle. Again, the fifths can go, can't they? Yeah, we'll leave them, but they can go for the angle, but we need them for the speed. So that's good. I will get rid of that negative because we've already got pointing down. So angle then is going to have to be inverse tan of the opposite, which is the 21, over the adjacent 112. What does that give us? Let's have a look. I'm in degrees, which is good. Inverse tan of 21 on 112. I get 10.6. It looked like a 6 too much. 10.6. Is that good? Did they want the angle? Do they want tan of the angle? Let's find out. If I do 21 on 112, is that answer? 21 on 112, I get an answer of, yeah, okay. So this is all correct. They just want the actual like 21 on 112. Do you mean was the answer? So let's rewrite this ever so slightly. Tan theta is 21 on 112. Lovely, looks good. For the speed then, what we're going to have is, well, the fifth can come out the front, can it? And then we're going to have 112 squared plus 21 squared. And that whole thing square rooted. Wow, that calculator, what do we get? 0.2 times by the square root of 112 squared plus 21 squared gives us, not a very nice number, 22.8. Is that right? It is indeed. Lovely. This is all looking good. What question was that? 5. Is there a 6? There is. Yeah, I didn't know on this one. We had some, I'm guessing it's like a rod being held up by something. I don't know how. And the question doesn't really change, I don't think, if they're pointing in or pointing out. Because like when we go to resolve the forces horizontally, it's the identical equations. It's just like, is this one pointing left or is it pointing right? Do you mean when you resolve them? I don't think it makes a difference. I think we were told this, that tan alpha was 15 on 8, which seems very strange, but I didn't see any other way that it kind of appeared in the mark schemes. So it says like just as assuming that this is true, so I'm not sure exactly where that came from. First thing I want to do though is find K. So we have some mass over here. We don't know how many times heavier it is on the rod itself. What can we do to find that then? Well, we'll take moments about A, because that's going to mean that we have only like known forces. The other unknown is at T. So if we can take moments about A, it eliminates that force from T. So from our moments equation. Moments about A, we'll go clockwise first. Well, it's going to be equilibrium, isn't it? So what's taking us clockwise? How long was this thing? It was A long, wasn't it? Or was it 2A long? Yeah, it's 2A long. Let me write that up there somewhere. So it's 2A all the way across. Uniform as well, wasn't it? So that is in the middle. That bit. I think that was one of the assumption questions, maybe. No, ignore me. So yeah, going horizontally, we have A mg plus 2A k mg, and that's going to be equal to 2A 17 mg on 6, and then times by the angle that we need is going to have to be sine of beta. Sorry, this should be tan of beta up here, not of alpha. Yeah. Excuse me. So yeah, we needed to get sine of this. So what's this going to tell us about sine? Is that it is going to be, well, let's draw the triangle out. It's not so easy to see that one, is it? We have the opposite is 15, the adjacent is 8. So doing 8 squared plus 15 squared. What do we get? 289, square that, 17, and yep. So sine opposite will be 15 on 17, and the cos will be 8 on 17. I think that's one I've seen before. Maybe I have, but I just don't recognize it. So that's good. We wanted to have sine. We didn't have the angle in between us. So 15 on 17. Again, very nice with 17 on the top, 17 on the bottom, because they will go away, won't they? This is good. We can cancel lots of things out. Everything has an A. Everything has an M. Everything has a G. That 17 can go with that 17. Let's see what we're left with. So there's just a 1. We have a 2K. On this side, there's a 2. I've got a 1/6, and I've got a 15. So this, that was 3. Altogether is 45. Take away the 1 is 44. Divide by the 2 gives me 22. So it's quite a lot heavier. 22 times heavier. Have I done that really wrong? What's gone wrong there? Sorry, that's a third. It's a third. Ignore me. Yeah, that's a third, not 3. So that's 5. And then taking away the 1 gives us 4. Divided by 2 is 2. Lovely. Looks good to me. Looks good in the mark schema as well. Next, we then find T. Find that tension. Lots of ways we can do this. I think the easiest probably is just resolving forces. Like we know everything now, don't we? So if we just resolve them horizontally, like eliminate as many things as we can from here. So yeah, let's look at things going horizontally. What's pulling us to the right? I'll use the black ones. Like you can see how this is not going to make any difference if we did the purple ones. But doing to the right, then it's going to be T cos. Cos is 8 on 17. Lots of T. And that will equal then, we're going to have to do cos of beta. Oh, sorry. Oh, yeah, ignore me. It's going to be slightly different. That was for B. So it's going to be 17 mg on 6 times by the cos, 8 on 17. And then we don't know for T, do we? So it's going to be T cos alpha. Let's simplify this a little bit on the left first before we move on. 17s will go. Bop, bop. 8 on 6 is 4 on 3. So we've got 4 on 3 is equal to T cos alpha. That looks good. Let's have a look at doing this vertically. So a similar sort of idea. We're going to have T sine now. pulling us up. We're also going to have the 17 mg on 6 times by its own sign. So 17's go, 15 on 6 is going to be 5 on 2. So plus 5 on 2 mg. And we'll just double check that. 17 on 6. 17 on 6 times by, what am I saying? 15 on 17. Yep, 5 on 2. And then pulling us down, we have 1 mg, another 2 mgs, 3 mgs. So t sine altogether then, if we do that subtraction, just taking the 5 on 2 away, what do we have is exactly 1/2 of mg. So we know what t cos is, we know what t sine is. We want to work out t. This is like harmonic stuff, like r cos theta plus alpha. So if we square everything, add it all together, we're going to have t squared, lots of cos squared and sine squared, so it's just 1, goes away. But we'll write it down, so like t squared cos squared plus t squared sine squared. Well, the first line is going to be 16 on 9, yeah. That should still have an mg, sorry. Should still have an mg. An mg squared. And then do another one, we'll have a quarter. Mg all squared. So what is 1 quarter plus 16 on a 9th? We have 37 on 36. No, 73 on 36. So square rooting that, what do we get? Root 76. Root 73 on 6 for t. Lots of mg. Lots of mg. Does that look good? It does. Looks very good. I think that's the end of mechanics. I'll take a little break and then I'll do the stats. Yeah, lovely. Right, first one of the stats then. We're given some Venn diagram, aren't we? I think the only thing you're told is that A and B are independent, and then obviously these different values and stuff. Mutually exclusive, quite a few we can do. So A and C, well, just A and C actually, just A and C. A and C. Mutually exclusive just means they don't cross over, yeah? You can see the A and the C circles, no intersection between the two. Finding P. Sorry, we were also told one other thing, weren't we? We were told that the probability of A was equal to 0.3. So we were also told that. So using that, we can see that P plus 0.18 should be 0.30. So it's 0.12 left over here. 0.12. Probability of B. From there, did we know anything else? We knew they're independent, didn't we? So what we can say, the intersection, the 0.18, should be equal to the probability of A, which is the 0.3, times by probability of B. So that's going to tell us probability of B should be 18 on 30. So it's 60%. Does that look good? That looks very good. Circle these are correct. Next one then, find Q. I think in that case, if we just add up A and B, so A we knew was 0.3, B was 0.6, so that's altogether 0.9. Taking that away, we've got 72 left over, so it should be 28 on the outside, is it? Yeah, nice. That looks good to me. Probability of B given C. So if we're inside the C circle, what's the chance for inside the B circle? Well, we're stuck inside there, aren't we? C is a subset of B, so therefore, like if you're inside C, you are inside B, so it's 100%. Other way around, we need to look at the intersection of B and C. Oh, the probability of B. So doing that intersection, 0.15. B was 0.6. So altogether, we get 0.25. Does that look good? Yep, looks good to me. Lovely jobbly. Next one. Yeah, here I can only get the answers, do you know what I mean? So I don't know what they're actually asking about. But it should have said opportunity or convenience sampling for the first one. Something about now we have a binomial hypothesis, don't we, going on? So things about like the assumptions what you need for binomial, or like why is this not going to work for something. So we had there might not be independent with everything you were doing, and then the probability might change as well. One reason why it might not be, probably even I to be faulty, it says here. So you've got some machine, I'm guessing, making parts maybe, and the probability might change over time. So we're doing a hypothesis test to see whether the probability is bigger than 0.015. We're given a test statistic of 3 and a sample size of 65. So if we go through and look at the probability of it being less than or equal to 3, oh, sorry, first thing to do, actually, what's the mean? Like, what is our expectation of our, let's first write down what is our distribution. So it's distributed binomially, 65 and 0.015. So the mean, like the average value that outputs, is 65 times 0.015. What does that give us? 0.015. We get an answer of 0.975. So we do need to be looking at the upper end. So the probability that x is bigger than or equal to 3. Looking on the calculator, what does that give us? It gives us 0.0744. And we were told to use alpha. Our significance level should be 0.05. So our value we had is bigger than 0.05. So therefore, there is evidence to reject H0. We've seen so many faulty samples, like 3 out of 65 is way more than having like what's effectively 15 out of 1,000, is it, I think? Or is that 15 out of 10,000 maybe? But either way, much less than 3 out of 65. So that's good. Number 3, I'm guessing large data set stuff to begin with. You had millimeters and then 0 for the answers. Doesn't say anything on here about what they're for, where they come from. Next bit, we had some values. So we wanted to work out the mean and the standard deviation of these. Yep. So for the mean, we're going to go through and take the sum. So 506.8, divide it by 184, and that gives us a value of 2.75-ish. For the standard deviation, we're going to take the big number, the 10750, sum of the squares, divide it by how many there are, so 184, and then take away that mean that we just found but squared, and then we'll square root the whole thing. Whack that in the calculator, you get 7.13. These are all in millimeters, so I would still write down the units if they don't give them to you. We're now given, I don't know exactly what's going on here. We've got some hypothesis tests about there being rainfall and then it increasing. It doesn't really say too much about anything. I think you were just given the p-value, this very small p-value here, and then asked the hypothesis test. Look, this is just so small. You're like, p is just really small. P is very small. So therefore reject. H0. Yeah, this would be 1 in 10, 1 in 100. That's 1 in 1,000, 1 in 10,000. Yeah, 15 in 10,000. So it's such a small possibility. Like, you've seen such a small amount of it happen. You're like, okay, it's just, we must think that there's been an increase, or yeah, the chance of what we've seen has been so unlikely that we must change our mind, basically. Yeah, that's good. On here then, again, I'm trying to piece this back together. I'm assuming the graph looks something like this, where you've got some time, you had some like centimeters, some like distance or height or something. We are asked some questions. What we're asked for the first one, not sure. It should be positive. Sorry, positive correlation in there. And we're given some line of best fit, I'm guessing, for this blue one. And we want to tell us what does like the 39.6 mean in that. So it's going to mean every second that we take, we're going basically 39.6 centimeters. You can always look at the units, like that's the gradient of a straight line. So it's centimeters per second. It's our speed basically, or like whatever this is, if it's speed or like rate of growth or something like that. I mean, it's the change in the length or the distance or whatever this is measuring per second. Yeah, an increase for each increase of 1 second, y increases by 39.6 centimeters. Finding when y is 4. I think we managed just to read through using the equation and doing what's it going to be, 39.6 times by 4 plus the 52.4. And that gives us about 211 when we round it to 211 centimeters. Is that an over and under estimate? So we had this, I'm assuming this is roughly what the shape is going to be. So we can see our line of best fit was above the actual data that we had. So our line of best fit has been an over estimate. comment on this, and it's just saying like this is where I've pieced together like kind of rough shape of this, because like we did have a big R value. Apparently, we were told that R was equal to 0.97, so it's a very strong correlation, but the data is quite clearly not linear. But this can still happen because like you just end up with so much data that's very close to being linear, but it's actually following this quadratic path. So it still looks quite strongly correlated, and it still obviously still is, but it just actually doesn't fit a straight line model. So what they've said in here, yeah, although this is strong positive linear correlation, the scatter diagram shows a curved pattern, so non-linear model may be more suitable. And then like suggest a better model, they said x squared. So because of that suggestion for the answer, I've assumed that it's been like roughly this sort of shape for what's going on. Lovely. Next one. What's going on here then? We have some spinner, and we either got heads or tails. What's happening again? So I'm trying to piece this back together. Like I think we had some spinner, and you get either a head 2/5 of the time or a tail 3/5 of the time. And we were looking at the distribution of the second head. Like what number spin did you get the second head at? Why is this not binomials? Because the probability is always going to change. You don't have enough fixed number trials either. Do you know what I mean? So it's like, yeah, not fixed n, not fixed n, and p may change. Or p does change. P changes. P varies. What have they said? Yeah, number of spins is not fixed. I'm assuming the probability it will change. Do you know what I mean? Like the chance of it being number one, you just can't be the first one, can you? So that's 0. So hopefully it does happen at some point. Do you know what I mean? So it should vary as well. Either of these should be fine. I think this is the one that was written in the book. Chance of us getting the second head on the 4th spin. So we need to have had one head out of 3 spins. So we must have had like heads, tails, tails, or those 3 in some other order. The probability of each spin on the spinner is independent. Like there's no history here. Do you know what I mean? We just spin it and we get this value. So all of these have the same probability. We just work them out once and then we just times it by 3. So the probability of getting any of those things is going to be 3 times the probability of getting one of them. Let's say heads, tails, tails. And to get that, then we need to have one heads, so 2/5, and then 2 tails, so 3/5 squared. Why that calculate them? What do I get? 3 times 2/5 times 3/5. Ooh, let's not have fractions and fractions. Times 3/5 all squared gives me 54 on 125. Is that good? No, it should be 108. Why not times by 2 somewhere? Oh, okay. Okay. Ignore me. Yeah, this is good. This is good. So that's the chance of us getting to the 4th spin, and we've had one head so far. So we need to times this by the chance of getting the next one being a head. So it's going to be that number times by the chance of getting a head, 2/5. So it's 108 over 65. So just to clarify, this is the chance of getting to the 4th spin, and you've had exactly one head so far. And then we times that by the chance of getting a head next time to give us the chance of having the second head be on the 4th spin. We know the distribution, finding the chance of us getting like all of the different values. We already know the 5th one. So let's make ourselves a little table. We can have x in one row, the probability that is equal to these values in the next. And let's have a look. So we need to do 2. So that's the chance of just getting heads. So it's going to be 2/5 squared, so 425. For 3 then, what's going to happen? Well, we need to, in the first 2 spins, get either a heads or a tail. Well, one of each, yeah? So it's going to be 2/5 times 3/5, but 2 different ways of getting that. So 2/5 times 3/5 times 2. That's the chance of us getting, so we've got 12 over 25 there. So let's just write this down. That's probably of getting heads, tails, or tails, heads. It's going to be 12 and 25. And then the next one we need is a head. So it's going to be 2/5 of that. So 24 on 125. For 4 then, let's have a look. What did we do? We did 4 already, didn't we? So that's one we did know. So it's 108 over 625. And then for 5, well, we need to have the chance of getting to position 4 and only having one head. So heads, tails, tails, tails. And then all the different possible arrangements of that. How many are there? Well, the head can be in 4 different places. So four different ways. Doing that then, we're going to have to do 4 times getting a head, 2/5, times getting a tails, 3/5. But doing that 3 times, what do we get? 4 times 2/5 times 3/5, all cubed, gives me 216 on 65. 216 on 625. Does that look good? Nearly. This one doesn't. Oh, good. Again, I've just got to, I need to times that by the 2/5, don't I? Times by 2/5, what do we get? Not the correct answer. What's gone wrong? Is this all right? Did I type everything incorrectly? Let's double check. The answer scheme that I've got here may well be wrong as well. So let's have a look. Is that correct in what we need to be thinking? Get to number 5 and have just one heads. So you get a head, and then you times it by getting a tail 3 times. So 4 times by 2/5, because you're going to arrange it in 4 different ways, times by the 3/5, all cubed. Gives me that, yeah. So this sum is correct, and then it's times by 2/5. So I'm getting a slightly different number. I'm getting 432 over 3125. Sorry, I shouldn't be there. That's when we times that number by 2/5. I'm thinking that mine is correct, just because when I look at the answer scheme that I have in front of me, it has 25, 125, 65, and then 625 again. Like they've timed, these are all going up in 5s, but it doesn't go up in 5 there. And I don't know how that we would not go up in 5 there, because we times by the 5th, and at no point do we have a 5 on the top row. I think anyway, because I've done the pattern and like got it correct here. Do you know what I mean? So this one not being correct, I don't see any way I've done it differently for that next one than what I've done for these. Do you know what I mean? We do this. All that happens really is that's changed into a 4. That changes to a 3. That's it. Yeah, that's all that changes. That becomes a 4. That becomes a 3 to do the same process. 4. That's a 3. These are correct. Yeah. So this is what I've got. What the book said in front of me is 297 on 625. So not quite sure exactly where that's coming from. What is 297 on 216? 11 on 8. So there they've times by that. Yeah, it's times by 11 on 8. So I'm not too sure. I'm trusting my one, but this is what's written in the ones on here. Hopefully one of those is correct. I'm not entirely sure. I think it's the one that I've written down. Pretty sure it's the one I've written down. Part D then. Chance of getting 1 head and 4 tails. So probability of 1 head, 4 tails. So it's very similar to what we've been doing up above, and it chance of getting 1 head is 2/5. Chance of getting 4 tails will be 3/5 to the power of 4. But how many different ways can they be arranged? Well, the heads can go in any of the positions. So it's going to be 5. So doing that, what do we get? 5 times 2/5 is 2, yeah. 2 times 3/5 to the power of 4. I get 162 on 65, which is the same as the mark scheme. So yeah, I'm thinking what I've done here is correct. Do you know what I mean? I think everything I've done so far has been right. I think it might be one just little mistake in that bit. This looks good to me. The problem that we have 1 head, given that we're on the 4th one. Well, what did this mean? X equal 4. What did that mean? It means that we got our 2nd head. The 2nd head on the 4th spin. But if you've only had 1 head, was it just having 1 head or the head being first? I think it's the heads being first. So like the number of heads we've had is 1. Do you mean? So I think that should be like the modulus of h. Let me rewrite that a bit neater. So the amount of heads that we've had, number of heads might be better. Number of heads is equal to 1. So how can we have 2 heads on the, like, once we've got to 4 spins, we've had the second head. Well, the second head appears on the 4th spin, but we've only now had, we want the chance of now having 1 head. So that's 0. It can't happen, yeah. If we've had 2 spins, 2 heads, we can't have had only 1 head. I think, oh, okay, yeah, and that explains partly. So yeah, because just to clarify, what this is referring to is that we received the second head on the 4th spin. And then we're asking for what's the chance that we've had only 1 head so far. I think you could replace this 4 with any number because it's going to refer to the fact that, yeah, we've got the second head. So we can't have 1 head now. I think that will make sense. I think that's nice and straightforward. Is that the end? No, there is one more. Some normal stuff. Is it just one more? Yeah, just one more. Some normal stuff then. We're told the distribution, but we don't know the variance or standard deviation. But we do know that when we have the central, we have 540 is the middle. So 10 centimeters either side or 10 somethings either side is 80%. And we know that the sample size should be, we have some sample size later on for 250. Let's find sigma then. I think that's going to be like sample mean. Yeah, we're going to do a sample of these things. Okay, so first bit, finding this then, we're going to need to do the inverse normal, inverse standard normal. So doing that of 0.4. No, yeah, no, 0.1, 0.1, sorry. Because think of what does it mean if you're the middle 80%. You've got 10% on the left, 8% in the middle, 10% on the right. So we want to find like this number using the 530. So that should equal to 530 minus mu of 540 over sigma. So we can see sigma is going to be 10 or minus 10 over whatever we get from doing the inverse calculator stuff. Doing that, what number did we get? They do it slightly differently to me, I think. Yeah, they do. Let me use my calculator quick. Inverse normal. If you've got one that you can actually do, like if you can do it with unknown bits, then lovely, you do it that way around. But generally, you don't have one of those. So it's going to be minus 1, yeah, minus 1.2816, blah blah blah. So theta itself, sigma should be equal to 7.8. 7.803 if you want to be a bit more precise. That looks good though. Now then, what is asked about the mean actually? No, we want the okay, yeah, we want the expected amount of them that are going to be less than 530 when we take a sample of 250. So we've got this distribution. We do it 250 times. How many do we expect to be below 530? Well, this is the middle 80%. The probability of being below that 530 is 10%. So it should be this 10% of them. So if we're trying 250 times, the expectation should be 25 of them, given that sample size. That looks good. Down here, then we get a new distribution, 275 and 11 for our sigma. Probably that this is above 263. Just whacking the calculator, yeah. Nothing tricky about that, I don't think at all. Not being silly, am I? No, not being silly at all. 0.862. And then we do a hypothesis test. So we do have a sample mean. Sample, so we do 36. We have this distribution. We do it 36 times. We get a sample size, well, a sample mean of 271.7, which is quite far from 275. We want to see if there's a change in it. So you can see, obviously, like we are on the left-hand side, the lower value, like we have a lower, an observation was lower than the actual given mean. So if we're looking for a change, it will be the left-hand side we're looking for. Yeah, so even though it's going to be, I don't know exactly then what they've done, do you mean? So the way we're going to draw it out, we'll have this distribution, 275 in the middle, and we had 5% down there. And our question then is whether our 275, so the 271.7, is that there or is it there? So let's have a look. If we work out the probability of our distribution being less than 271.7, remember now that we're looking at the sample mean. So actually, if we write down what that's going to be, the distribution will have the same mean itself, so of 275. But now we need to, like, it gets shrunk in. Do you know what I mean? Like, everything's going to go this way and gets kind of like, you imagine if we had a massive, if you did the entire population, you should get that your mean is exactly in the middle because it becomes the population mean. Do you mean as you do more samples, the more samples you do, closer to the population it becomes. So we need to basically divide this down. We're going to have the 11 squared on the top still, but we'll divide it by the sample size of 36. So as we use that, what do we get for this value? We get 0.0719. That's bigger than 5%. So our value was like here. So it's not in the critical region. So we're going to not reject H0. Yeah, that looks good. This paper was not too bad. Do you know what I mean? This was all right. As long as you're fine doing the sample mean stuff, should be okay. This is the weird one, wasn't it? This is the most weird one. If you didn't understand what was happening, it can be very tricky. I imagine a tree diagram would have been like your best friend if you were not sure what to do with this sort of stuff, and if you weren't happy with like permutations. Do you know what I mean? This is just a tree diagram. It's just me looking at like, okay, I can either go like heads or tails, and then I can go tails and tails, or on the next one I can go tails and heads, and then get like the opposite one to figure it out. And it's just looking at all those three different paths to work out like what's this number. But you can imagine it gets a bit tricky looking down on some of these. I mean, they become quite long-winded. This one, hope not too bad as well. Just correlation in it, nice and straightforward. Same here, just pulling these numbers. Hypothesis test came up quite a few times, didn't it? So if you were not comfortable with those, it would be a bit tricky. This stuff again, not too bad. And probability, yeah, as well, not too bad either. This you can do with working out, like, actually just see what is the intersection of both. It's just the same as seeing it, so just counts it down to 1-on-1. And this stuff, yeah, not too nice, but it's not the worst in the world. You just have to be aware of like, where do we take the equations from? Which equation is going to be easier to solve? Do you know what I mean? It's like knowing that we had to take them around A to solve it, because then we get rid of the tension to find the unknown mass. And doing the simultaneous on these bits and kind of recognizing that, okay, we don't actually need to find the alpha, so we can do like the square stuff to get rid of it straight away. This, again, nothing too weird there, as long as you understand how to find like the time first and then work with it from there. This stuff, again, not too bad if you know how to split them up. If you ever see this question again, always just treat them as different objects. It doesn't really matter how they are placed together, just what forces are they being, like, what forces are they feeling basically from the relationship they have with the other things. This, again, not too bad, just making sure that you're aware kind of like what's the best way to resolve the forces and like to compare the forces going on. Thinking when we want to find R, we get rid of X, so we'll go the perpendicular way, and then we know everything, so it doesn't really matter a huge amount for the next one. But you can see like we picked horizontal because it's just got X just by itself, not doing some angle of X. This stuff, again, not too bad, was it? As long as you understand which way round, make sure you're not differentiating when you should integrate. And again, nice and straightforward to start. So yeah, overall, but it's pretty good, wasn't it? Not too bad.